All right, so fun making aside, this is my visual aid for the day, which I would like to point out took me, what, Seth? Maybe a minute and a half to make? So let's all agree that there wasn't a lot of time invested in the visual aid, I'm sorry. We didn't have a ready-built paddle wheel and the 3D printers on the fritz, so this is what you got. So this thing is to illustrate the geometric definition of curl. Okay? So envision that there were air circulating in the room, right? If I thought about putting this at a point, right, so I'm going to pin it here at the kind of middle of the paddle wheel in space. And then if the air is circulating, right, this thing is going to tend to settle out in the direction, what?
That the air is flowing.
Yeah, it's going to tend to settle out in the direction that the air is kind of eddying around the point it's sitting at, right? You see that? And as long as I only let it spin one way, oops, and I'm spinning it backwards. That way, of course, being the right-hand rule way. Duh, because, right, the only thing we use to establish orientation is the right-hand rule. So if I've got this in right-hand rule orientation, like it can only spin according to the right-hand rule, it'll settle out to this thing where the circulation's happening this way. And what's the relationship between the circulation and the axis? Yeah, the axis is perpendicular to the kind of plane in which greatest circulation is happening. You guys see that? So this thing is going to be your illustration in your head for geometric curl. Cool. So what was the old definition for curl? So curl of F, the vector field. How did I calculate it?
Two-dimensional.
Yeah, so there was a 2-dimension and a 3-dimensional version. Let's go with just the 3-dimension. So what was the 3-dimensional version of curl? How did I calculate that?
That was cross upside down triangle thing.
Perfect. Upside down triangle thing crossed with the vector field, right? So this is the calculation style definition, right? You take nabla, which is that partial with respect to x, partial with respect to y, and partial with respect to z. And then you cross it with whatever your vector field is. You guys cool with that? That makes some kind of horrible gobbledygook, right? But what that thing means geometrically, and this is why we do this thing, the geometric definition is that curl of F is a vector field. Does that make sense that it would be a vector field?
Yeah, it's cross product.
Perfect. When you cross product two vectors, right, you're going to get a vector. This one's a function, right, of x, y, and z. This thing's just partials, so it's not going to change the fact that your result's going to be a function of x, y, and z, and it's going to be a vector valued one, right? You see that? Yeah. So I'm definitely getting a vector field out of this thing. And that curl of F, the vector field with two properties. One, it points along the axis of that little paddle wheel thing. So let's see if I can draw one of these. So points along the axis of the little paddle wheel deal. Right? So there's going to be your direction. Cool. Now what else should a vector have? It's going to have a direction, right?
Magnitude.
And it needs a magnitude, right? So how long is the vector going to be that point? Like, how long is that? What's a good interpretation?
The speed.
Yeah, it should be the speed with which the little thing is going to spin, right?
So almost a better way to look at it is a pinwheel, and the shaft on the pinwheel is the axis.
Yeah, perfect. And that's exactly what this thing is, right? Pinwheel would be a very nice prop for this. Cool. So it's a pinwheel. It's got that rotational axis. That's pointing along this guy. And And then the speed is going to be the magnitude. Of the pinwheel deal. Cool. So there's your geometry. Questions, things?